So I was thinking about what we should do in these next few classes. I was thinking we could have 4 or 5 lectures that are sort of seminar style about the 4-dimensional theory. You know, so if we start doing everything at the level of detail we've been doing in class, we won't go very far. However, there are some things I think you should just know about. Okay, so I was thinking that maybe we will go through 3 or 4 different topics for 4 dimensions, seminar style. By seminar style, I mean I will try to explain all the ideas, but we will not obsess about algebra. Okay, so so today we can have the first of these lectures. So today's lecture is based on this paper called by Intelligator and Vect. Okay, the archive number is 0304128. Okay, fine. So, in this paper we return to, so in these seminar style lectures, we'll have a couple of those on n equals 1 theories in 4 dimensions, a couple of on n equals 2, and then maybe I'll give you 1 lecture on n equals 4 Young-Mills theory. Just so that you have a sense of the supersymmetric, a rough sense of the supersymmetric landscape of n equals 4 theories. For 4-dimensional theories. Okay, so in this lecture we return to the study of n equals 1 superconformal supersymmetric theories. In particular, this lecture will be focused on n equals 1 superconformal theories. Now, let me give you 5 minutes of motivation for this focus. Okay? Let us step back and ask ourselves how quantum field theories are defined. Okay? Now, the way that, how quantum field theories are defined in some mathematically precise sense, nobody knows. One abstract way of trying to define quantum field theories is through some operator product expansions or some Whiteman axioms and so on. And that may prove useful at some point. But from practically, the way when we do calculations, when we think about quantum field theory, the way most physicists think of quantum field theory, in the way taught to us by Wilson, Polchinski, all of that. And the idea is this, that a quantum field theory is defined by a renormalization group flow that starts in the UV by a UV fixed point, at a UV fixed point, and then goes into the IR somewhere. Now, this somewhere in the IR could be many possibilities. Okay, it could be an IR fixed point. It could be a massive theory. It could be a free theory. Free or almost free theory. Okay? And of course, let's say we're looking at well-defined things. It's not a theory with a bad vacuum or something like that. Okay, these are really the possibilities. Okay? A massive theory, well, that's great. In the deep IR, it has nothing. Oh, some topological sector. Fine. An IR fixed point, this is always very interesting. You've got a flow from a UV fixed point to an IR fixed point. We'll come back to that in a minute. Free theory, this is the kind of thing that happens, for instance, in this is the kind of thing that happens in QCD above the asymptotic freedom bound. If you somehow manage to define it in the UV, then this thing will flow to a free theory in the IR. We've seen examples of all of these in the study of Seiberg duality, right? For instance, pure n equals 1 Yang-mills flow to a massive theory in the IR. N equals 1 Yang-mills in the conformal window flow to a conformal between 3 by 2, where NF was between 3 by 2 NC and 3 NC, flow to the conformal field theory. And then between NC plus 2 and 3 by 2 NC, NF in that range, it flowed to an IR free theory, which was but was IR free in the magnetic variables. So we've seen examples of all of this. Now, why am I saying all of this here? There were 2 points I wanted to make. The first is that even though IR behaviors of quantum field theories can be very plentiful, UV behaviors, where we use the term quantum field theory, at least in current usage of the term, is always a fixed point. And the point is this, that you see, if you take some effective field theory and try to somehow continue it to the UV, typically that effective field theory, as you go to higher and higher energies, violates unitarity. You need some behavior in the UV that can go all the way without violating unitarity. Okay? And we essentially know of 2 ways of doing this. First is that it goes to a conformal field theory in the UV. Second, that it goes to string theory in the UV. Okay? Well, what we call quantum field theory is a system without gravity. Okay? So effectively, maybe I'm misstating in complete detail, but effectively the only way we know in a quantum field theory, in theory without gravity, to be UV safe, to be a theory that is well defined in the UV all the way and never violate unitarity, is that it comes from a quantum field theory. But if you're going to have to flow an infinite distance, okay, then you better be a conformal field theory, because where do you go at infinity otherwise? Okay, that conformal field theory could be a bit generalized, could be free theory. So in the UV you could start with a free theory or a conformal field theory. Okay, so this general idea that quantum field theories are defined by RG flows away from either free or conformal field theories is a very useful way of thinking of conformal field theory, of the space of all quantum field theories. Could be that in the end, when we learn more, it becomes a bit inaccurate. Okay, but it's a very useful way of organizing your thoughts. Because of this, there is these conformal field theories, well, free theories are simple, right? We can write them all down. What's not so simple is non-trivial conformal field theories. These play a distinguished role in the space of all quantum field theories because, in some sense, they are the mother of all theories. All theories arise, what that we call quantum field theories, arise in the UV from conformal field theories or free theories. Okay? This is one reason to be specially interested in these conformal field theories. Because if, for instance, you are able to classify all conformal field theories, then you've taken the important first step towards classifying all quantum field theories. Because you take these things and their flows and you get everything. Okay? So this is one good reason to be particularly interested in superconformal field theories. There is another reason, which is it sometimes happens, as we've seen here, that you have a flow from one superconformal field theory to another. Okay? And so sometimes conformal field theories determine the IR behavior of theories. This is often of great interest. As you know, in the study of statistical mechanics, for instance, phase transitions are governed by IR conformal field theories. So both from the point of view of the UV, in some sense, conceptual sense, especially from the point of view of the UV, but also from the point of view of the IR, conformal dynamics is often extremely interesting. Okay? So, this is one bit of motivation to focus on the study of superconformal field theories. There is another practical reason to focus on the study of superconformal field theories. And the practical reason is that you can say more about these theories than about ordinary supersymmetric theories. As you remember from the representation theory lectures that we had, there are some exact statements you can make about scaling dimensions in these theories and so on. Okay, today's lecture is about one other such, about facilitating making these exact statements. So, what is the question addressed in this paper? The question goes this way. As you remember, part of this supergroup in 4 dimensions was SU2, 2 / whatever, but since we're looking at n equals 1 supersymmetry, /1. Okay, there was this SU4 block, and then U1 block, and then the if you remember in the way we thought about these supergroups, roughly speaking, this was the 4 cross 4, this was the 1 cross 1, this is where the supersymmetries lay. 4 of them are Qs, 4 of them are Ss. Okay, this is the U1 R judge. This is SU2, 2, which is the same as SO4. 2. This is the conformal group in 4 dimensions. Okay, so you remember that the superconformal algebra for n equals 1 theories took the structure, and in particular, you remember that it always had this U1 R symmetry. Remember that for superconformal field theories, unlike for supersymmetric field theories, R symmetry is not optional. It's part of the symmetry algebra. It appears on the right-hand side of the commutator of 2 Qs. So it would be inconsistent if that symmetry was not in the theory. Okay? So so the first thing we can say about n equals 1 superconformal field theories, they always have an R charge. Good. Now, if you remember, in our analysis of Seiberg duality, a key role in that analysis was played by identifying the correct R charge. Okay? You remember that what we did was we had this naive R charge, and then we had this U1 axial symmetry. And we found that both the naive R charge and the U1 axial symmetry were anomalous. But there was one linear combination of them that was not. Okay? And that linear combination we identified as the correct R charge. But that was a very fortunate circumstance, because we had only 2 symmetries, 2 sort of chiral symmetries, U1 symmetries in our theory. Okay? This U1 R charge and the naive R charge and this U1 axial. There are 2 symmetries and 1 anomaly. So there was a unique non-anomalous charge. But in more generality, one could imagine a situation, okay, and there are many such examples, some of which we might take a look at, but one could imagine a situation in which you have a naive U1R, and let's say S different flavor symmetries. Okay, U1, let's say 1, U1, 2, up to U1S. Okay, for instance, if you had, well, it doesn't matter, we'll look at examples as we go on. But you could have many different kinds of matter, each one has its own kind of symmetry. It's easy to concoct such examples. Okay, now, in this situation, we have the same kind of question. We want to find each of these symmetries in general is anomalous. Okay? Each of these symmetries is anomalous, but there is one equation, one constraint on this thing, such that the right-hand side of the anomaly vanishes. So here we have a total of S plus 1 different symmetries, one equation. So we have an S-dimensional vector space of possible non-anomalous symmetries. Okay? Of possible non-anomalous symmetry. Okay? One of these, what? This is any vector in this vector space will be non-anomalous. No, this number will be the number because you see, when we compute the anomaly, let's say we compute the anomaly for this guy. Okay, so we get d mu, j mu, and this is j mu QCD of the QCD current. Okay, the anomaly that is just not allowed. The theory makes no sense if it's not zero. Okay, will be equal to, let's say, AR times F wedge F. Sorry, d mu j, this is j let me suppose that the j, let me take this linear combination. Let me say these have been given with some standard normalization. Okay, and let me make a trial j, which is sum over AR JR, this is AR JR plus sum over S AS JS. Let me compute its anomaly. Okay, so we have d mu, j mu. So I said it wrong. We're not looking at the anomaly of QCD. We're looking at the anomaly of this current, but the right-hand side is F wedge F of QCD. Okay, so we have d mu, j mu is equal to AR times, let's say, some BR, which is the number that you compute when you compute trace this representation times QCD square. You know, the kind of thing we've done many times. Okay, plus AS BS, sum over S times F wedge F, where this is QCD. Right, we'll get an equation like this, where ARs are the things we are unsure of, we want to fix. BRs are some given numbers. Right, for instance, if there was only one adjoint field, it would be 2n, that kind, right? Right, fundamental was 1, those numbers, right? Okay, and this has to be 0 for it to be a real symmetry, because the U1R symmetry is a genuine symmetry. Cannot be anomalous. So we conclude that AR BR plus sum over S AS BS is equal to 0. But you see, this is one equation on S plus 1 coefficients. Any choice of A's that satisfies this one equation gives you a non-anomalous symmetry. Okay, this defines an S-dimensional vector space of possible coefficients. Any one line in that vector space will give you a non-anomalous star symmetry. So if non-anomalous nature was your only constraint, then you don't really know what the R symmetry is. Now, why do we want to know about the R symmetry? Well, you remember we had, for instance, unitarity relations. You remember we had unitarity relations that told us, for instance, that delta was greater than equal to 3 by 2 times the R charge. This played an important role in the study of Seiberg duality, if you remember. Gave us a check of the idea that we reached that superconformal window, helped us demarcate the ends of that window, all of that. Okay? And this is an important thing. It gives you exact results for the scaling dimensions of some operators. Sounds very important, right? Very rare in a conformal, in an interacting theory, you have exact results, scaling dimensions of operators. But the point is, you know delta if you know the R charges. So for the short operators, delta is equal to 2 by 3 R, great. So you might think because R is some global symmetry, I can look at the Lagrangian and know its charge, the charge of the operator. But unless you know which symmetry in the Lagrangian is the R symmetry, you're out of luck. You don't know, right? So the question here is the following: which of the possible non-anomalous symmetries is the true R symmetry of the theory? Okay, that is the question these guys are addressing.
What happens to the other symmetries?
They're just flavor symmetries. They're symmetries of the theory, but they're not what appear on the right-hand side of the supersymmetry algebra. So they don't determine dimensions and so on. Is this clear? So this is a question we're addressing. How do we answer this question? Okay. Remarkably enough, you might think, if you were just given this question, you might think, okay, you can ask questions, you don't always get answers, right? You might think, okay, this is some very detailed, you have to do some Feynman diagrams, take something like that. Remarkably enough, that's not the case here. You can answer this question in a simpler way. Okay? And this is what I want to try to explain to you. Okay. So let me in my discussion, let me follow their the discussion in their paper and get to it. Okay. So the first thing in their paper is this. They give you a review in their paper, they give you a review which I think will be useful for us of currents and anomalies. The technique they're going to use is supersymmetry plus anomalies. Okay. Okay. So let's see. Okay. So the first thing they remind us of is the following. They remind us that if you have two currents, and one of them is inserted at x and the other is inserted at 0. And I want to find the inner conformal field theory. No supersymmetry needed for this point. I want to find the two-point function of this object here. They remind us that conformal invariance is completely sufficient to determine the functional dependence on the right-hand side. Is this something you guys are familiar with? Are you comfortable with this, or would you like an explanation of this? This is something you are. Well, first let me ask you, are you aware of the fact that two-point functions of scalars are completely determined by conformal invariance? And can somebody tell me why that's the case? So can you say that in a little more detail? Which part of the symmetry? Okay, excellent. So let me put together what Diksha, Karthik, and Chintan said. Let's say we were looking at scalars. Say OI, OJ. Let's say this was x and this was 0. Okay? Now, this guy, by translation invariance, we could call y, let's say. Okay, by translational invariance, a function only of x minus y. By rotational invariance, function of only x minus y is whole thing squared. And let's suppose this guy had dimension delta, this guy had dimension delta prime. By scale invariance is clearly 1 over x minus y, the whole thing, to the power delta plus delta prime. Okay? And if we had only rotation, translation, and scale invariance, that's where we'd stop. However, you know that there is a little more. That only operators of the same dimension can click. Okay? And that comes from demanding invariance under special conformal transformation. So equivalently, demanding that scale invariance continues to work, scale and translational invariance continues to work after inversion. Okay? And when we put these constraints here, that tells you that this form is not only determined, but these two can only click at equal values. Okay? Now, if you try to do a similar exercise here for these currents, okay? If you try to do a similar exercise here, once again, things can only depend on x minus y. Okay? And once again, currents, the great thing about currents is that there's no delta. You don't have to, there's no abstract delta. The scaling dimension of a current is what? Somebody tell me. D minus 1. Why is it D minus 1? Del mu, therefore?
Current Q is integral of
Excellent. Excellent. The integral of J gives you Q, which is a number. So integral over space for a current is dimensionless, scale 0. Okay, it's conserved, it doesn't change. Okay? Therefore, J itself has dimension D minus 1. Okay? So these guys here are dimension D minus 1. These guys have dimension D minus 1. And so let's see what kind of structures one could write down here. Okay. One could write down, now they're working in 4 dimensions. D minus 1 is 3. Okay. So you could write down the following. You could write down del mu, let's say, del square of del mu nu, okay, with an A plus a B times del mu of 1 over y x minus y to the power 4. Okay, this has all the properties you want. It transforms correctly under rotations. It has the right dimension because it's 6 on the right hand side. 2 derivatives. You might ask, what about x mu minus x nu? Could that appear? But that's exactly what is produced by acting on 1 over x with the del. So that's not new. Okay? So just rotations, scale invariance and translations will tell you this. Now we have 2 choices. At this point we can either act with special conformal transformations that will give us the answer, or we can do something even easier in this case because we know the current is conserved. So we can act on the left hand side with del mu. Okay? That gives you something from there and something from there. So it gives you a relationship between these A and B coefficients. Okay? So if you undertake that exercise, you will get tau ij by 16 pi to the 4 del squared delta mu nu minus del mu del nu. Yeah. Can you see by eye that if I act on this with del mu, we get 0 because this becomes del square and this becomes del mu. Okay, so clearly this is the right combination. Okay, so conservation plus scale invariance and everything else uniquely determines this. Then you can also check that it also obeys the special conformal transformations. Okay, so it's not some very mysterious thing. So the form of this is this form. The 16 pi squares, pi to the 4 is of course a convention. One important thing that we will use later on is that this tau ij here is a positive definite matrix. Okay? And that follows from unitarity. You take the 2-point functions of equal currents. The right hand side should be this with a positive number. Okay? One way of thinking of how this works about is from the state operator map. You can map the 2-point function to a norm calculation with insertions, and the norm calculation will be proportional to this tau ij. Is this clear?
Sorry, just to
yes.
So initially you wrote it as a linear combination of two tensor.
Yes.
And one of them was a singlet and one of them was the symmetric, and there is no antisymmetric because of the OP.
How make an antisymmetric? How will you make it? You can't antisymmetrize del with del. Yeah.
This is symmetric, but
No, I think Chintan was asking why did you? Chintan's idea was you have 2 vectors.
yeah.
Let's do the tensor product. Okay, you take two vectors, you do the tensor product, you get singlet, symmetric, and antisymmetric. Where's the antisymmetric? Well, with this content, you just cannot make it.
With the derivatives.
You cannot make it. Okay, yeah, it's true also that that's a statement about the OP, but this would be one derivation of that fact. Okay, fine. Okay, so this is one thing that they remind us of. Tau ij is symmetric, yes, because ji jj is the same as jjji. Of course, it interchanges x and y, but you see that because there are two derivatives, that goes away.
Depending on the dimension, tau ij can be symmetric or antisymmetric.
Why do you say that? Oh, you mean this? No, but this will always be mod xy. It will be square root of, yeah, because x minus y doesn't mean anything. Okay, excellent. Okay, so this is the first fact they remind us of, which we will keep track of. Okay, now, okay, it's a bit boring to go through all these facts. Okay, maybe I'll start the argument. Maybe I'll start the argument and we come back to these facts as and when needed. It's a little too boring. Okay. So, the first point that these guys make is the following. See, suppose now I have this true R current, JR, and then I have the remaining S minus 1 flavor currents. Let's call them JI. Now all of these have new indices. Okay. First question that this guy asks is, in a supersymmetric theory, what kind of multiplets, okay, do these currents sit in? Okay. Now, this, of course, has been much analyzed. I'm going to give you the answer, but let's try to make it plausible first. First, let's take J mu R. Okay? J mu R generates the R, its 0 part generates the R symmetry. But the R symmetry is just one term in the superconformal symmetry. So clearly, J mu R should lie in a multiplet that also includes generators of conformal invariance. But what are the operators that are used to generate conformal invariance? The stress tensor. Well, the stress tensor, right? So clearly, J mu R must lie in the same multiplet as the stress tensor. Okay? Therefore, this guy has to have a particular multiplet structure. Okay? The genuine J mu R, the one we don't yet know. Okay? We're just doing some background analysis. Okay. Excellent. So, this guy must lie in a, okay. Now, the multiplet that does this is a multiplet whose first term is a vector. Okay? These guys write that multiplet in the following language. They write it as T alpha alpha dot. Okay? Because alpha alpha dot combine to give a vector index in 4 dimensions. The lowest term in this multiplet is a vector. But now this T alpha alpha dot is also a function of theta and theta bar. Okay? And the term which goes like theta theta bar of this will have a term with 2 alphas and 2 alpha dots. Right? Because each theta carries an alpha and each theta bar carries an alpha dot. So the coefficient will have 2 alphas and 2 alpha dots. And so we'll have a piece that is a symmetric tensor. Okay? So if you take this multiplet, the lowest term the bottom of the multiplet is a current which is J mu r. And the terms that appear higher order, higher up in this expansion, the terms that appear higher up in this expansion include the stress tensor. In fact, the supersymmetry currents will appear with 1 theta, 1 theta dot, because they are currents generating a spin half charge. So they have mu and alpha. Right? So current generating a spin 0 charge just has a mu. Current generating a spin half charge will have a mu, and the charge itself has an alpha index. So mu and alpha. So the Q's will have two alpha indices and 1 alpha dot index, the J for the Q, whereas the J for the Q bar will have 1 alpha and 2 alpha dot indices. Is this clear? So this super multiplet here has in it the stress tensor, the currents that generate supersymmetry, and the R symmetry all in one multiplet. Lowest component is the R symmetry. Second component is the supercurrents.
Q doesn't have mu, right? I think the spinor indices will be antisymmetric, right?
What? Q, the charge has 1 spinor index, but the current that generates that charge has a mu. Okay? So just like the lowest, the R symmetry has no indices, yet its current has a mu, right? And one way of thinking of the stress tensor is that it's the current for translations. That's why it has 1 mu index because it's a current and another mu index because it's translation. That's why it has 2 indices. Okay? So this field here is the multiplet that carries the R symmetry current, the stress tensor, and the supercurrent. Now, let us suppose the R symmetry is of the following sort. Okay? That when we compute the anomaly coefficients of the R symmetry, we get trace R cube is equal to K R R R. Now what does this mean? Here what we are doing is computing del mu J mu of the R symmetry current with 2 F mu nus also coupling to the R symmetry current. Okay? In that computation we had to insert representation, triple and take a trace. That whatever that is, and then that gave us a number. This was the thing that was 2n for the adjoint and 1 for the fundamental. Whatever that number is, I'm calling trace R of R cube. The anomaly coefficient for J mu R with background fields which are FR. Okay? Let us suppose that whatever this was KRR, this anomaly coefficient. Okay? Now, let's suppose that trace R, okay, is defined by KR. Now, this is something that I have not really talked to you about, but we didn't really use it in our discussion of Seiberg duality, though we could have. And that is that there is a kind of mixed anomaly, which is a mixed anomaly between flavor and gravitation. Okay? The kind of question that is in field theory is this. If you compute del mu J mu of a flavor current, and you couple the field theory to a background metric, then instead of getting some trace F wedge F on the right hand side, you could get a trace R wedge R. You might ask me, what does R wedge R mean? Well, R is some 4-index object. Think of it in Wehrbein language. When you think of R in Wehrbein language, it has the same structure as a field strength for the SOD transformations of local rotations of Wehrbeins. This is something you all familiar with, right? Okay? So in that language, R wedge R makes perfect sense because it's just R for an SOD gauge field. It plays the same, it's nothing special about it. Okay? So when one does the when one does the when one looks at matching anomalies, this is another anomaly one could match, which is what happens to the current when we turn on a background metric for the theory on which our theory lives. Okay, but now because the stress tensor is something that couples universally to all fields, there's no other information needed. There's no representation information needed. You see, when we were computing, let's say, the anomaly due to some F wedge F of some non-abelian global symmetry, we needed to know what representation of that non-abelian global symmetry our particle transformed in. And that gave us this 2n for adjoint, 1 for. But everything transforms the same way under gravity. Everything carries energy. Okay, as long as it's got the same current structure. For that reason, this gravitational anomaly, when you do the calculation, is determined just by trace R. The thing on the right-hand side is just the same for everything.
But
Go on.
spinors and scalars will transform differently than Taylor transform.
Spinners, but everything here is the same spinor. You see, we're only doing this one loop diagram for chiral fermions. Only thing that contributes to the anomaly is the chiral fermions. But all chiral fermions couple the same way to gravity. It's true that were we doing this calculation in string theory? Have you guys gone through the anomaly you have. You guys have. Anomaly cancellation calculation in string theory. Then the 5-form field strength contributes differently from the fermions to the gravitational anomaly also. But here we're doing a baby example, just quantum field theory in 4 dimensions. Only things that contribute to anomaly are chiral fermions. Okay? Clear? You remember that this R matrix was this matrix which we're taking is the matrix of charges of chiral fermions. Okay, all good? So suppose that this thing determines the coupling del mu j mu is equal to R wedge R on the right hand side. Okay? It's governed by an anomaly coefficient, let's call that Kr. Whatever it is. Okay? And now we could also look at trace of R squared Fi. Okay, where Fi is one of the flavor currents. One of the flavor currents GI. Okay, and whatever this is, we will call it KRR Fi. And finally, we could be interested in trace R RFIFJ. Okay, and we give this another name, KRR, that's RFIFJ. Okay, at the moment we're just giving names to various anomaly coefficients. Is this clear? Okay. Now, what does this anomaly coefficient tell us about the divergence? Okay, we're going to ask, we have this lovely stress tensor current multiplet, this T alpha alpha dot. And we want to compute the divergence of del mu j mu. Or really, we'll do the superfield analog of that. Okay, computing the divergence of del mu j mu, okay, of of this this current multiplet. Okay. Now, what does this thing tell us about? That? So the question I'm going to ask first in components. Suppose I have J mu r, and I compute del mu. Okay. The fact that there are these anomalies. Okay. The fact that there are these anomalies. Okay. What does it tell us about this del mu J mu here? Okay. So the way to think of this is as follows. See, this del mu J mu r included, for instance, from this term, something, this k r r r times f r wedge f r. Okay. And it included k r and let's call it gg for gravity, r wedge r, and similar other such terms, including flavor terms and so flavor field strengths and so on. Okay. Now, basically, the statement of these anomalies, okay, is a statement of what this is. There are the other two also. You have to write this term and this term as well. Okay, it's basically a statement of what this is. Okay, so if we know the anomalies, we know what del mu J mu is. We know what del mu J mu is, and then we can try to rewrite that in superfield language. Okay, so let me tell you what the final result is. Of this multiplet. No, you see, when you know what this information is sufficient to determine it for the whole multiplet. Right, because it's in the same multiplet. Right? So you know what it is for this component, and then you write down a superfield expression that will have the right expression, will reduce to del mu J mu for this thing. And that completely determines it for the whole thing. This is really a key point, Sunil. It's sort of the key point that different things in the multiplet all, tell you about each other.
And then you can explicitly verify that the other ones.
That the other ones, exactly. You could explicitly verify that. But that will follow immediately just from supersymmetry. Exactly. Okay. So let me tell you now in a little more detail. One way of writing this thing is to write this del is what we called D. Okay, and it's a covariant version of what we called D. Okay, so del alpha dot of T alpha alpha dot is equal to del alpha LT. Turns out this is the case. Okay, where this LT is equal to okay. So what are all these things? Right. What are all these things? Okay. Okay. When I write W squared, okay, this object here is let's first go to this guy. First go to this guy. This guy here is something very simple, something we're familiar with. This W is the field strength multiplet for the gauge field coupling to the ith flavor symmetry. Okay, so this W here is the field strength multiplet for the gauge field coupling to the ith flavor symmetry, and these guys here, these W's and these sigmas, are sort of field strength multiplets. These coefficients are whatever they are. They will be built out of these anomaly coefficients. We'll come back to that in a minute. Okay. Whereas these guys here, this W squared and these sigma squared, are sort of field strength multiples built out of the graviton. Okay. So if we had done the kind of analysis that we did for superfields, but for gravity, okay, then we would get W's whose field strengths were curvatures. Okay, so this thing here is where this is a thing that appears in the supergravity expansion of in the expansion of gravity. Okay, doesn't matter. Details don't matter here. This is why it's seminar style. Okay, there are lots of things that we just want to get the main point. Then one can go back and look at the algebra. Okay, and the sigma, I'm just writing down a formula. Sigma is this. Plus something else you can build out of gravity. It's related to the Euler density. Okay, doesn't matter. You get something. We're going to use this very little. I wrote it down just to contrast it with what we're actually going to use. Okay, the answer for del dot J of the R symmetry current can be written in terms of the field strength multiplets for flavor charges. Okay, and the gravity stuff itself. The gravity stuff itself, of course, contains the R symmetry field strength as well, because it's the same multiplet as the stress tensor. Okay, so this is a beautiful formula and actually has a lot of information, but we're going to use it almost not at all. Okay. Yes. You'll get contributions in general from all three terms. Yes, and that will because we should have got an RRR term. We should have got also an R, then gravity term. We should have got flavor term. So everything contributes. Okay, and these terms, these C, A, and tau ij are linear combinations of these various coefficients that appear here.
Sorry, why is gravity field strength and U1R field strength because of the super?
Because the super multiplet that carried their current had both T mu nu and J mu in it. Therefore, the thing that couples to it will have the gauge field for gravity and the gauge field for this R in the same multiplet. Okay? As I said, we're going to use this very little. I put it up here mainly so that you know that it can be done, and to contrast it with the sort of simpler equation that we're going to use in just 1 minute.
So graviton is in both these
Yeah. These W and sigma are two different terms made out of the same multiplet. Okay? They're both made out of the gravity multiplet. Okay? But two different structures arise on the right hand side. Okay? Related to the fact that there are different anomalies here. There's this guy and there's this guy. So the two pieces of data. That's like two structures. Is this clear? Okay? Fine. So this is what we get. Yes, actually it is the same as that. Now the reason for that is that why is that? Why is that? Just give me a minute. Yes. The reason for that is that you see, is basically this, that if you want to know Tj goes like J, okay, this OP is completely determined by the charges of J, and therefore by the 2-point function of J. Yes, in general in conformal field theory. Okay, if you have T O goes like O, that OP is completely determined just by the charges of the operator O, and the charges you can read off just from the 2-point function. So the data that is in the 2-point function O with O is not independent of the data that is in the 3-point function TOO. Okay? Therefore, but the 3-point function TOO, so it's a good question, let me say. First, what is the connection between what I've said here and the 3-point function? Okay? Suppose I have an object, so let's simplify, all this is very complicated, but suppose I just had del mu J mu is equal to F wedge F, where F was the gauge field coupling to the same J. Suppose I had this. Now, suppose I want to get some information about the 3-point function of J mu, J alpha, J beta. One way of doing that, remember, A is the source coupling to J. So if I differentiate this twice with respect to A, that turns this 1-point function into a 3-point function. Okay? And then this equation tells us that del mu of this 3 point, and after differentiating we're supposed to set A to 0. If we want just some statement about the 3-point function in the presence of 0 sources. The usual thing, right? You put sources on, you differentiate with respect to them, and then set sources to 0 at the end. So this gives you information not about a 2-point function, because if you differentiate, you get rid of one of the A's, but there's an A left here, so you'll just get 0. But for 3-point functions, you can hit this A and hit this A. Okay? And so you will get two derivatives left, because this was d mu A mu. Okay? And then you'll get delta function. You'll get a delta function that tells you that all three had to be at the same place. Okay? So I'm saying it very schematically. but there's some delta function that forces all three to be at the same point. And there's some derivative structure here. But the important thing is that there is the same information in one particular contact term, in d mu, j mu, j alpha, j beta, and this coefficient here. The coefficient of this contact term is the same as the coefficient of this object here. So, if you know the 3-point function of three currents, from there you can reconstruct this anomaly part. Is this clear? I'm sorry the lecture is so, but I hope it's clear. Please stop and ask questions if something's not clear. Is this clear, Sunil?
Yeah. But left-hand side, you can compute using the 2-point function, right?
That's the first thing is that the left-hand side here is just some 3-point function data. Okay? Now, on the other hand, if we did the same analysis for Tjj, because the Tjj 3-point function is determined by the Jj, that's completely determined in terms of tau. Okay? This is why the part of the non-conservation of the stress tensor current in terms of Jj is actually determined by that same tau ij. Okay? All of this to make it clear, to get these formulas is a lot of work, as you can imagine. But you see the logic, right? Okay? Excellent. Okay, so we're done with that equation. It's an equation that is very useful to know exists and has many interesting consequences. Okay? But we're actually going to focus on the simpler next equation. Okay? Okay. We're going to focus on the simpler next equation, which is, what about the analogous thing not for the R-symmetry current, but for the flavor currents. Okay? Once again, using what we know it should be for components, and then supersymmetry, writing down a superfield expression and so on, you can work it out. Okay? Turns out to be the following. Let's see if we make sure we understand what all the terms mean in this equation. First, Wi, we are looking at the flavor current Ji. Its field strength multiplet is Wi. When we write Wj, it's the field strength multiplet with respect to the flavor current Jj. Okay? So, what about Kii? Well, here I only wrote down the anomaly coefficients for the R symmetry, but there are also the anomaly coefficients for the flavor symmetries. Okay? So, trace of Fi cube will be Kii. Trace of Fi Fi squared Fl will be KIIL, and so on. Okay? So these are the various anomaly coefficients. What is Ki? This is trace of Fi, and it's relevant to the gravitational anomaly of the flavor current, of the ith flavor current. Okay? And what is W squared? Well, this W squared is the same thing we saw there. It's the gravitational field strength multiplet. Is this clear? Anything on this equation that you don't understand? Which one? Wi?
On the left hand side, the Ji.
Ji is this current. Function of theta theta bar. Everything here is a supercurrent. Okay? Something you could note for consistency is that Ji is, I should have said that, sorry, I didn't say it, right? If you look at I told you about what happened for R symmetry. For R symmetry, the current multiplet lies in a multiplet whose lowest component was a vector. Okay? Because it had to two up get you a 2 tensor. For flavor symmetries lie in a multiplet whose lowest component is a scalar. Then 2 up will be a vector. Okay? So Ji here is just that scalar. It's the lowest component of the multiplet that contains the flavor current. So I should have said that. I'm sorry. I forgot I hadn't told you that. Is this clear?
So this will be some chiral scalar.
No, it's a real non-chiral superfield. But because we take d bar square here, the left hand side is chiral, which is consistent now with the fact that everything on the right hand side is chiral.
And what will be so there the interpretation of the fermions was like was supersymmetry and the tensor was the stress tensor. So here what will be the interpretation of
Yeah, good. So when we go 1 level up, we get the fermionic current corresponding to the flavor symmetry. Actually, it's 1.5 levels up. You see, because it's a supersymmetric theory, every bosonic symmetry has a fermionic counterpart. Okay? So this is the multiplet that includes both that fermionic symmetry current as well as the bosonic symmetry current. Okay? Yeah. Okay. So excellent. So this is the structure of the divergence that you get from the multiplet, okay, of the ordinary flavor symmetry. Please.
The true R symmetry, which is non-anomalous,
Yes.
is the one which sits in the
Stress tensor multiplet.
But till now we have not figured out which is the true R symmetry, which linear combination. These Ks, are these Ks same as the Ks of A?
We don't yet know what these Ks are. Whatever this true R symmetry is, its Ks. The whole purpose is to figure that out. Right now we're imagining somebody knows how, and we're going to try to find constraints on that true R symmetry.
So these, the things we wrote on the left hand side were with the
True R symmetry. We don't yet know what it is, but whatever it is, it will obey this. Okay? Excellent. Okay, so this structure you understand, right? This part is the part that determines F wedge F for the same flavor. This is F wedge F involving different flavors. And this is R wedge R from the gravity multiplet. It will also include the R symmetry piece. Now there is something interesting here. The interesting thing is this, that when you compute this, you didn't find 2 gravitational structures. You found 1 gravitational structure. Okay? And this is just a consequence of multiplet structure, just follows from supersymmetry. Okay? Now that's a bit of a puzzle, because you might have thought that this guy is one coefficient. That gives you, am I saying it right? Yeah. This guy is one coefficient. That gives you that tells you how much FR wedge FR appears on the right hand side. And then there is a second coefficient. Okay, then there is a second coefficient which tells you how much gravity wedge gravity. R wedge R where R is the gravity, the Ricci tensor appears on the right hand side. That's how it worked upstairs, right? There were these two gravitational structures because there were two anomaly coefficients. Is this clear? Yes, the W and that funny sigma. Those were the two structures. And that's both of them have the Ricci R mu nu, that Riemann tensor basically. Both of them have the Riemann tensor, but there are two different structures that appear built out of the Riemann structure, Riemann tensor. And that made sense to us because if you took the R symmetry current, you computed del mu J mu R, there were two things you could have got. You could have got FR wedge FR, okay, and that came with a coefficient which was RR, KRRR. But there's a second thing you could have got, which is Riemann wedge Riemann, and that came with a coefficient that was KR. Because there were two pieces of data, there should be room on the right hand side for those two pieces of data. Now maybe you'll get linear combinations of them, but that's why you had two structures. That's roughly how we thought of it. The two pieces of data there went to the two pieces of data there. No surprise. However, you could have said the same thing here for this flavor symmetry current, because the del mu del mu J mu of the flavor has two possible structures coming from the gravity multiplet. FR wedge FR, which is Ki RR, and Riemann wedge Riemann, which is just Ki.
Yeah, but there W had both gravity and R symmetry.
Similarly, here W has both gravity and R symmetry charge.
But they don't correspond to the same multiplet. These
Wi does not, but W does. W is the gravitational multiplet.
So I'm saying in that case RRR and this R
In the earlier case, K R R R and K R determined what appeared on the right hand side in the gravity multiplet. So there are two pieces of data and two structures. All good. Now let us look at the flavor current and look at what appears on the right hand side in the gravity multiplet, the gravity field strength. Once again, there are two anomaly coefficients, KIRR okay. What? In general, we don't even know what the right R symmetry is. But in general, if we make some guess, it will be non-zero. KIRR and KI. One of them has Riemann wedge Riemann. The other has R symmetry field strength wedge R symmetry field strength. Is this clear? However, only one structure appears on the right hand side. And it's just a consequence of supersymmetry. This tells you that Ki and Ki Riemann, KIRR are not independent, because you can compute them both from the same piece of data. Okay, I've chosen to write that piece of data as Ki but I could have written it with some other coefficient as KIRR. Okay? So this thing tells you that there is a relationship between trace Fi and trace Fi r square. Okay? So it tells you that there is a relationship here between trace Fi and trace Fi r squared, and that relationship I'm going to write down for you. When you work it out carefully, it's 9 of trace r squared Fi is equal to trace Fi. Is this clear? The whole point of this paper is that the gravitational structure that appears on the right-hand side of the flavor symmetry current divergence, there's only one structure. Now, you know, this is an example of how you can get lucky. This is, in my opinion, a spectacular result. We'll come back to this. But it's an example of how you can get lucky in physics. If you look before 2003, basically this whole superfield structure was known. People had painstakingly, Osborne and collaborators, painstakingly computed the top equation. But somehow everyone thought that the flavor symmetries would be boring. And nobody had computed the bottom equation. Intriligate and Wecht computed it, I suppose, just for completeness, right? You computed it. And then they found a surprise. Surprise is that that second structure just didn't appear. So suddenly it takes what would otherwise have been, you know, some filling up of a detail in superfield algebra converts it into a really major result. Because suddenly you find that there is a constraint. Two anomaly coefficients that look independent are related if you choose the correct R symmetry.
This gives an equation for every I.
This gives an equation for every I.
Only the R symmetry is left to find.
Now let's understand what the structure of this equation is. Okay? Suppose I don't know what the R symmetry is. Okay? But I write it as, so there is, let's say, some, let us suppose that to start with there was a naive R symmetry and then the various flavor symmetries. But there was one ABJ anomaly equation, the one we started with at the beginning of the lecture. One constraint. So we can always put in, okay, we can always put in, solve that equation. So let's say that we have the trial R symmetry is, I don't know, give me some symbol, sum over phi I Fi plus whatever is needed of the naive R symmetry to satisfy the ABJ equation. There will be some linear thing in phi's plus R naive, whatever is needed to stay on that manifold. So I'm parameterizing where I am on the manifold by these phi i's. Is this clear? Now I take this in. So this is the R. I don't know what these phi i's are. I should use consistent notation. This is good. I take that and plug it into here. Okay? I take that and plug it into here. Now every term in this equation I know, because those trace Fi, Fj, whatever, I can compute. They're just charge matrices for the chiral fermions. So every term that I know, so it becomes an explicit equation. What kind of equation does it become? It's a quadratic equation. Okay? How many quadratic equations do I get? As many as there are flavor symmetries. How many variables did I have? As many as there were flavor symmetries. So you have as many variables as equations. Okay? And so this equation here gives you a set of equations whose solution determines the true R symmetry.
The variables are phi I.
The phi i's. So there are as many phi i's as i's, but as many equations as i's. Okay? And so because of that, you suddenly have gone from no knowledge of what the R symmetry is to almost complete knowledge. Almost complete because there may be many solutions to this equation. Quadratic after all. Okay? Okay, fantastic. Fantastic. So we've got our first constraint here. Could the equation have no solutions, you're saying? No real solutions, you're asking. It's a good question. Yeah. On physical grounds, that would probably tell you that the theory just was not superconformally invariant. Right? You guessed that it was superconformally invariant, but you made the wrong guess. It would be something like that, right? I think algebraically it might be possible for it to happen. Okay. Yeah. Yes. We needed to compute the superfield thing. Yeah, that was the main new contribution to this paper. They computed that. Never been done before. You don't care. Whatever the R symmetry is, it's in that W multiplet there. You see, here we're not doing a loop calculation or anything like that. You see, all these Ks and so on are of whatever the true R symmetry is.
Yeah, so these Ks and those Ks are different.
Why are they different?
Because those were the Ks.
It's true, it's true. In the sense that when we actually compute here, we will just compute a matrix of Fs, being agnostic as to whether it's true R symmetry or flavor symmetry. Is that what you meant, Diksha?
No, I was saying about the equation itself.
No, here it's the same, because here also we are saying this is for whatever the true R symmetry or whatever the true flavor symmetries are. We don't need the explicit values. It's all abstract analysis. Understand? Just the supersymmetry transform. The way they worked it out was to use superfield and found the only thing that was consistent with the component was this structure. Now, once you've done that, I haven't, but I'm sure there are many follow-up papers using supersymmetric word identities to show this. You know, superfields are convenient techniques, but you don't need them. But the point is that supersymmetry tells you that Ki and Ki Riemann are related to each other. The remarkable thing was that I think people had always assumed that the most special guy is the current that lies in the R symmetry multiplet. So when that didn't happen there, what is the chance it will happen here? But this is the remarkable thing. The fact that this was in a different kind of multiplet made its right-hand side tighter. You know, that equation was well known for many years, 20 years, I would guess. This nobody had computed. It's really, I find the lesson. You know, when I was a PhD student, David Gross was one of the people teaching us. And when people asked him questions he thought it was too philosophical, he would glare like this and say, compute, you know, and and that is the lesson. Sometimes in physics, don't think too much, compute. You know, human brain is limited. You can't anticipate everything. Okay, fine. Other questions? Or did I answer all the questions? You had a question left over?
Yeah, if you substitute this R there, you will again get K triple I, right?
You see, this equation has nothing now. This is just in terms of traces. So, for any basis of your flavor symmetries, you can compute all traces. K disappeared now. The point is there's the one structure. What the coefficient was will cancel out between this side and that side. Do you understand? The really important point, nothing else is important in this equation other than the fact that there's one structure. You can remove all the pi's and so on in that equation. Makes no difference. Only thing that is important is that there's a one structure. Is this clear? Okay? Let me say again, supersymmetry tells us, remarkably enough, that the anomaly coefficient, the Riemann-Wedge-Riemann anomaly coefficient of a flavor symmetry is related to the R-symmetry wedge R-symmetry coefficient of the flavor symmetry by a particular relationship. But if you have a guess for the flavor symmetry, you can compute these two coefficients independently. And in general, they're not related. So the guess that you make has to be one so that they are related. And that's what determines what your true R-symmetry is. Is this clear? Okay. Let us keep going. Then this equation will not be satisfied. So it tells you you've not got the true R-symmetry.
Suppose I read the whole analysis with some false R symmetry.
Yes.
I will not get this equation.
You'll not get this equation and you'll find this equation, you'll find an inconsistency. Right? Because you'll find the anomaly coefficient for your flavor current with R wedge R has a different coefficient from Riemann with Riemann, so it does not agree with the superfield structure. Okay?
This flavor symmetry in the boxed equation,
Yes.
is it the same as the flavor equation in the equation below? In the box equation, we separated out the true symmetry and the other flavor symmetry.
Yes.
The true R symmetry is a combination of the Niles R symmetry and some another flavor symmetry.
Okay. Good question. Good question. Good question. Chintan's point is that it looks like there's one equation less.
That equation also, del u j u of true R symmetry should be 0.
But there was no real relationship. Yeah, good point. Let me see what they say about this. I think, Chintan, it probably connects with the fact that these are hang on. Yeah, sorry. Yeah, give me a minute. Good question. Good question. I don't. Let's see. Give me 1 minute.
We still have the freedom to write FIs in terms of each other, right?
FIs.
True FI, I mean true FI, I mean what are other than the R's?
Right. Right. That's fine. But I thought your question was that I really should have one less equation, because this should be only true for the true FIs,
Yes.
not for the R.
Old FIs, sorry, the new FIs will now be, can now be written as linear combinations of old FIs. FIs and plus the R.
Chintan's question is the way I, at least what is puzzling me now is the following. I told you that the total number of equations we have is as many. See, suppose you had S flavor symmetries plus a naive R symmetry. Okay, so the total number of non-anomalous symmetries is S. Okay, and when I was working this out, and what they do in the paper is they say now we have S equations, but we also had S variables. Okay, Chintan's point is we should really have S minus 1 equations, because we have an equation for every true flavor symmetry, but not also for the R symmetry. Okay, so I think the way I'm understanding Chintan's question is that while you've got S variables, why do you have S rather than S minus 1 equations? Okay, this is how I'm understanding the question. Okay, and it looks like a good thing, a good question. Somehow one of the other equations should come. I don't yet know. Give me a minute. Maybe 2 minutes of reading this paper. Maybe I should have read the paper more carefully, but maybe 2 minutes of reading the paper will give it. Otherwise, next class I will tell you. It's a great question. Yeah, go on.
My question was that I was thinking we can find these coefficients by putting this capital R below in the equation above, right? Just putting it. Capital R is function of all symmetries, not just true flavor symmetry. And but these FIs and that FIs.
But the equation, capital R is a general thing.
Yeah.
Okay, but we have this equation only for true flavor symmetries. So I thought Chintan's question is we have S minus 1 rather than S equations. However, to solve you need S equations. Certainly in the paper they've asserted all S equations are true. Why?
Yeah, why are we having one less?
Because of the non-anomalous symmetry, S non-anomalous symmetries, one of them is R symmetry, and S minus 1 of them are flavor. S values, and therefore we are asserting S equations. But one was anomalous. So we should only be looking at in the subspace of non-anomalous symmetries.
I thought only one was non-anomalous. All others could have been anomalous also. Only the true R symmetry has to be non-anomalous. Flavor symmetries could have been anomalous also.
Could have been, but are not, right? Because we just compute the anomaly. We get f wedge f QCD on the right hand side for each of these things with some given coefficient. So there is one equation that determines that the anomaly is 0. So the non-anomalous symmetries are codimension 1 in the space of all possible symmetries. Okay? So the space of non-anomalous symmetries is S-dimensional. It's S-dimensional vector space. Right? Now, we're parametrizing this S-dimensional vector space. Maybe what I'm doing, maybe this is the point. Maybe the thing is, I'm sorry, the point is this somehow, is that I'm giving too much, this was the point. When I did this Fi here, this was homogeneous parameterization. Okay? What only mattered is ratios. So the number of parameters in this linear combination will be S minus 1. What?
Flavor symmetries and R symmetry.
And R symmetry. Then we've got a one-dimensional submanifold. We've got an S-dimensional vector space of coefficients. I have to parameterize a direction in that S-dimensional vector space. That is parameterized by S minus 1 values. Yeah. Yeah. Yeah.
The number doesn't, the coefficient doesn't matter.
The overall coefficient will not matter. I think that's basically at play here. Yeah. But I will think this through and confirm it next class. I should say it more clearly. I will check this. I will check this. Yeah, somehow I feel I've not given you the full answer to this question. It's a great question. I'll give me 1 more minute. I will see if I can find it. Otherwise, we'll just complete and I'll tell you next class. Okay, let's just complete the thing I will tell you next class. I feel I've not given the complete answer to Chintan's question. I will give you a better answer. Okay. Fine. Okay. Now the next thing to say about this equation. Yeah, so somehow we haven't completely understood the derivation, but I'm pretty sure this is correct. So let's go with it. Okay. The next thing to say about this is that there is a sort of interesting way to rewrite this equation, which is the following. Consider the following object. This functional built out of trial R charges. Okay? I give you a functional built out of trial R charges. Okay? And I ask the following question. I ask, what do I get if I extremize this function? Okay, so I extremize this function by changing the little coefficient of Fi in it, for instance. And I have to extremize it with respect to all the Fi's. Okay, so when I differentiate, this factor of 3 gives me a 9. I get trace RT squared Fi, because I've just changed the coefficient in front of that one Fi. Okay, minus trace Fi is equal to 0. And that's the same as that equation. Is this clear? So what I'm doing is I'm taking RT is equal to some alpha or whatever, I called it phi I Fi, and I'm differentiating with respect to phi I. Is that clear? So the small change in R is delta phi I Fi. I put that in. and I get this. Okay, and with respect to all variations with respect to each of the phi i's, I should get 0. So that gives me that equation. So this quantity here, if I extremize that, that's the same as this equation up here. But now there is something sort of interesting. And this something interesting actually follows from, in some sense, the stuff we've talked about, but I'm just going to tell you about it. And that interesting thing is that, this quantity that you extremize is a quantity we've seen before. It's not a new quantity. In fact, if you write this quantity 3 by 32, 3 trace r cube minus trace r. Okay, this quantity was some, so it's just a constant times the old quantity. This quantity here is a quantity that people had defined before and called A. Okay, and the reason this had been defined before, I'm now going to tell you about.
The title was maximization. Should we check about the second?
It's coming. One more thing. Yes. Okay. But first, let me just tell you what this A was. Okay. When in two-dimensional CFT, all of you know that the trace of T is equal to C times R. That's some 12 or 24 or something, proportional to. Okay? In a four-dimensional CFT, you can ask, what is the analog of this? Okay? Now, in a four-dimensional CFT, if you see, in a two-dimensional CFT, the trace of a stress tensor is proportional to some scalar of dimension 2. In a four-dimensional CFT, it should be proportional to some scalar of dimension 4. Okay? So it's some scalar you build. Now each Riemann tensor is dimension 2. Okay? So in a four-dimensional CFT, what you want is something on the right-hand side that is built out of Riemann tensors. Okay? Riemann tensors and has dimension 4, so built out of 2 Riemann tensors. Okay? And more seriously analyzing this equation tells you that there are 2 allowed structures on this side. Okay? One of which here couples to basically this Gauss-Bonnet kind of term. Okay, a Gauss-Bonnet kind of term. And the coefficient of that people call A. And then there is another term built out of 2 Riemanns that you can write down. Okay, just different basically different contraction structures. Okay, and this term here people call C, the coefficient. So in 2 dimensions, there's one coefficient for what the trace of the stress tensor can be. In 4 dimensions, there's one more. There's this A and this C. Okay, and something that people had shown before, Anselmi and collaborators had shown before, Osborne and friends, is that in a superconformal field theory, this A here can also be computed, okay, from anomaly coefficients of the R symmetry. And in fact, this was the formula for A in these theories. Okay? How this comes about, let's postpone for a moment. This is something that people had established. Now, something else that people had conjectured at that point was, there was this, in 2 dimensions, there's this very interesting property of the C object here, which is that it always decreases under RG flows. Right? The Zamoylikov C theorem, established beautifully and simply and so easily by Zamoylikov in the 1980s. A question that had come up in the 90s is there an analog in four-dimensional field theories? And Cardy, by studying various examples, conjectured that the analog of the sum logic of C theorem was the A theorem. Okay? Is that A always decreases under RG flows. By now this has been proved. Schwimmer and Komargotsky proved it, 2010, 2012, something like that. But at the time this paper was written, that was still conjecture. Okay? So this A, there was this feeling that somehow it is the natural analog of these two coefficients. This one is the natural analog of what appears in 2 dimensions. Okay? And so what these guys observed is that their condition is the condition that A is extremized. And now finally we come to, okay, and we'll come back, okay, we come back maybe at the beginning of next class as to how this connects with the RG flow business. Okay, but let us first turn to maximization. So far we've only looked at extremization. Let's now turn to maximization. Okay. So let us now compute, okay, let's now go back up here to that more complicated relationship. Oh, in fact, we don't even need that relation. Yeah. Okay. Let us now go back to this question that we had talked about before. In fact, in response to Sunil's question. The question was the tau ij that appears in the, okay, let me remind you. There's del mu j mu r, okay, del mu j mu r. This had a tau ij divided minus by 40. F by f. This tau ij was the same as the tau ij that appeared in the 2-point function of currents. Why is that? Well, del mu j mu r, right hand side, is same as what we get from del mu of the Riemann tensor, the stress tensor, because they are in the same multiplet. But that we argued was determined just by the 2-point function coefficients. Okay? So this you could get from that equation up there. But we can see on general grounds that it should be determined by tau ij. Is this clear? The important point here is that this tau ij has positivity properties. Okay? So why is that of interest to us? This equation here tells us that K R I j is equal to tau ij, right? Because this, by definition, is the anomaly coefficient you get when you compute the current j mu r, and you get the contribution from I and j. Okay, so this equation tells us that this is and if you work it out, minus tau ij by 3, whatever, the 3 doesn't matter. Okay, so this is great. But you see, this quantity is the second derivative of R. You take R trial and compute its trace. So suppose we take trace R trial cube. Okay, you take trace R trial cube and you compute its second derivative with respect to variation of the flavors. You will get trace R trial Fi Fj. Now, this second derivative of this is same as second derivative of that, because the second derivative of the piece that is linear in R is 0. So this second derivative, the second derivative of that of our functional is same as second derivative of this quantity, but that is proportional to a tau ij which has definite positivity properties. Okay, trace through the signs, and you find that this is not just extremized, but is maximized. All eigenvalues are positive. Okay. Lastly, the last thing I want to say, and then we can stop today's lecture and go for lunch, is this. You see, what is the connection between what is, at least intuitively, the connection between what we've done and this idea that A decreases under RG flows? Okay, so imagine a flow from one fixed point to another. Let's say the UV fixed point has some number of flavor symmetries. The R symmetry is obtained in the UV fixed point by maximizing over all possible R symmetries in this big space. That's what we said. By maximizing this A over all possible R symmetries in this big space. Now, imagine turning on a relevant operator that will eventually end up in a new fixed point. Typically, that relevant operator breaks some of the flavor symmetries. So, when we go to the IR theory, once again we should compute A by maximizing over all unbroken R symmetries. But it's a smaller space. So the maximization will be less efficient, so we'll get a lower value. That is the basic intuition. That the fact that it's not just extremized, maximized, okay, seems to be in good fit with this idea that A always decreases. Now, there are two problems with this argument, now, as the authors note. The first is that the maximization was done locally, not globally. Okay, so the argument doesn't quite stand. And the second is that it sometimes happens, as Intriligator very well knows since he was involved in some of these studies, sometimes happens that in the IR and RG fluid, there's a new emergent flavor symmetry. That's not something that was there all through the flow, it just emerges in the IR. So, this goes against, because now you could have enhancement of symmetries. So, it's not a clean argument. Having said that, it does feel that it fits well with that basic idea. These other things seem a bit like exceptions. Okay? And of course, now that we know that A maximization, that A does decrease under RG flows, we understand that their argument for it was quite prescient. Right? Okay? Last thing I want to say, and then we'll stop. The last thing I want to say is that notice that A is obtained by maximizing over possible values. Now, that maximization involved some quadratic equations, which gives things like square roots, but not very complicated answers. Okay? So this tells you something something interesting in structure, that all superconformal field theories, 4 dimensions, have A's that have a certain number theoretic structure. Intriligator calls them algebraic numbers. I don't really know what those are, but I suppose it means like surds, like a plus square root of an integer, that kind. Okay, this is also very interesting. Why is it very interesting? It's very interesting for the following reason. You see, in the study of C equals 1 minimal models in 2 dimensions, one of the great results of that study is that all scaling dimensions and all central charges were rational numbers. Of the space of all possible real numbers, you single out these rational numbers, telling you something very special is happening, and was connected with the fact that these were solvable theories. Right? The fact that we're getting some interesting number theoretic properties of potential central charges of all n equals 1 superconformal field theories holds out somehow the promise that these theories may one day be solvable. There's something nice about that, right? Okay, so that's it. That's all I wanted to say. I will come back to Chintan's question and see if I have anything more clearer to say about it. Okay, but let's take a 1-minute summary. Well, 1-minute summary was that the whole thing was actually very, very simple. The whole thing, the 1-minute summary of the paper is that for flavor symmetries, the anomaly with Riemann wedge Riemann on the right hand side and the anomaly with R symmetry wedge R symmetry were not independent of each other. And that fact gives you equations for what the R symmetry could possibly be. Hugely constraining possibilities, and generically just completely determining it. Okay, so as we go on in our studies, we will see that there is a known analog of this phenomenon in 3 dimensions. It's called F maximization. The true R symmetry of 3-dimensional theories also determined by a maximization principle, or maximization of something. That something is the 3-sphere partition function. We will come to that. We'll turn to that. So again, in 3 dimensions, we have this principle somehow for determining. I don't know of anything like that in higher than 4 dimensions. Anything known about such things.
If we have a quadratic equation, what if both the solutions are physical?
What if all solutions are local? There are more than one solutions that are local maxima. First, I would have to. I think they claim that this uniquely determines the solution. That at least one of them will. That there will not be more than one local maximum. But I have not personally checked it. Again, I what? No, saddle points. Yeah. Yes, but most of them are saddle points. That they go this way in some direction, but that way in other directions. That's a generic behavior, right? You know, if you have n variables and as an extremum, 50% chance it's a maximum, 50% chance it's a minimum. So the chance that you get a maximum is very small. Right? You have to, it's 1 over 2 to the power n. Okay. Why is that? Because it was the same thing that appeared in the right hand side of the JJ 2-point function. Okay? And JJ 2-point function can be related to norm of JI insertions. Okay, great.